Okay. First of all, Almudena and I would like to thank the SOC for giving us the opportunity to talk about this and present some of the highlights of ALMA discoveries in the study of nearby AGNs. In fact, ALMA can emit the central regions of nearby active galaxies with spatial resolution for just a few parsec. And so these observations can be used, for example, to verify the validity of unifying theories of AGNs, but also to understand the feed-in and the feedback cycle of the gas in these objects by resolving the distribution and the kinematics of molecular gas with exquisite detail. So unifying theories of AGNs that were initially put forward but in this seminal paper by Antonucci and Miller interpret the wide variety of properties of AGNs in terms of the nuclear obscuration of AGN radiation by a parsec scale dusty molecular torus. So AGN radiation would be absorbed, in particular in the UV and in the optical domain, and these photos would be reprocessed into the infrared, and also this tori would contribute to the X-ray absorption and reflection. So now the question is whether do we have any evidence, direct undisputed evidence that this dusty molecular tori exist in real galaxies? In fact, for high resolution infrared observations, there is evidence of a parsec scale emission of hot dust, and I mean by hot dust temperatures of around 500 to 800 K. And there is also evidence of emission on larger spatial scales of tens of parsecs aligned with the polar direction. This is what is called the polar dust component. Although this field is rapidly evolving and there are really fantastic changes in the field brought by instruments like Matisse in the mid-infrared or gravity in the near-infrared, there are limitations in infrared observations of this type. And these are due to the fact that there are few baselines, limited UV coverage. So there are no direct imaging of the sources. All the results rely on the modeling of visibilities, and this can be tricky. Okay, ALMA can counterbalance to a large extent these observational limitations, and this is thanks to the large number of antennas, more than 50, and the associated baselines of the order of 1,000. So the fidelity of the images obtained by ALMA is really fantastic. So ALMA can emit directly this dusty molecular tori near AGNs with high fidelity, as we said, with spatial resolution of just a few parsec, and also using several frequency bands. In contrast with infrared observations that we already said are sensitive mostly to hot dust and gas, ALMA is sensitive to cold dust and gas, and also sensitive to a wide range of physical densities for molecular gas. The question is whether this component, relatively cold, might represent very likely the bulk of the mass in these compact disks. ALMA has IFU capabilities, so it's sensitive to the kinematics of the gas. We can probe the internal dynamics of molecular tori, and we want to know if these disks are stationary rotating structures or they are affected by non-cyclic motions, particularly by outflowing motions that have been invoked in some theoretical scenarios, like the disk-wind scenarios of Elitzer and Schlossman. ALMA can also emit the connection of the torus with the host. If there is any connection, we want to know if tori are isolated or connected to the disks by inflowing or outflowing structures. We have to underline, I think I would like to underline that these molecular dusty tori are one of the very last steps before the gas gets accreted onto the black hole. So understanding the nature of these disks is the key to understanding the feeding and the feedback cycle of gas in active galaxies. So it's not a detailed thing, it's really a fundamental thing. ALMA has already been able to study in detail the molecular tori in a handful of objects. And the first is the prototypical Cipher-2 galaxy NGC 1068. So we were able to use ALMA in cycle 2 to emit the emission of dust, continuum emission with a spatial resolution of 4 parsec in this galaxy. So we were able to provide the first evidence that this dusty tori exists in AGNs. In this object, we emit the emission from dust as coming from a 7 parsec diameter torus. So the first surprise is the size of the torus. It's 7 parsec. So this is a factor of 5 larger than the size derived from infrared observations. So this calls for a change of the parsec scale torus paradigm. The torus is bigger than expected. That's the first surprise. And these results have been also nicely confirmed more recently by imaging the molecular torus in several molecular lines, CO and ACO plus lines. And as you can see, we confirm the existence of this big torus with a range of diameters from 11 to 28 parsec. The important result here is that thanks to the fact that we are probing the torus with different molecular lines which are sensitive to different densities, around 4 orders of magnitude difference in physical densities, we see that the lower densities probed by the CO2-1 line give larger sizes for the torus. So we see many phases, the many phases of the molecular torus. The torus is not a monolithic unique structure. It has a layer structure. So ALMA has been able to resolve the density radial stratification inside the torus. Of course, the higher density traces like the 423 line of HCO plus give a different picture because the torus gets shrunk and a smaller size. Concerning the kinematics, you might expect that the gas in the disk is dominated by rotation because we're not that far from the sphere of the film lens. And in fact, there is rotation, but there is also outflowing motions. And in fact, we interpret these non-circular outflowing motions due to interaction of molecular gas with the aging wind on this very small scales. We built a 3D kinematical model, morphokinematical model of the gas inside the torus. And in fact, also morphologically, you already identified this kind of X-shaped morphology that gives you the impression that the gas is being pushed by the aging wind through thermal pressure of radiation pressure and is leaving the torus at some point. So our models estimate that half of the mass inside the torus is being affected by this aging feedback. This is not the only case of outflowing torus. Although objects that have been studied by ALMA, like NGC 5643 and NGC 1377, show signatures of these outflowing motions. And this is in line with predictions of simulations of radiation-driven dusty molecular outflowing tori. So there seems to be a growing agreement between these very detailed observations of ALMA and the most recent dynamical models of molecular tori. So the lesson here is that aging feedback is helping to regulate the feeding in molecular tori. So this kind of self-regulation mechanisms, because as you can interpret, this is part of a self-regulation tool. The torus is not isolated, it's connected to the circumnuclear disk, and it's connected through outflowing gas lanes. And this is revealed by this spectral signature we identified along these structures. In fact, this outflow is identified on much larger scale. There's a large scale molecular outflow. So there's the outflow in the torus, in the connecting structures of the torus to the circumnuclear disk, and the circumnuclear disk itself on scales of 100 parsec is outflowing. So we see the signature of the footprint of aging feedback on a wide range of spatial scales. Of course, if you want to stay clear from the unique object syndrome, you need to look at other AGNs, and this is one of This is the purpose of NUGA survey, which is a first attempt to improve the statistics, the number of AGNs that are studied with this detail. NUGA is a survey of CO and continuum emission in 7 luminous AGNs with 4 parsec spatial resolution, with the aim of imaging AGN structures on this very nuclear scales, but also to connect and image the possible link of these structures to the hosts. The results of this survey have been published in a couple of papers that appeared by the end of last year. And that's just to give you a very quick update of like something like NUGA results in a nutshell. We do detect molecular tori and AGN continuum in 6 out of the 7 targets. So NGC1068 is not the only AGN where we do see this molecular tori structure. The sizes and the masses are large, of the order of 10 to 50 parsec, masses of 10 to the 6 to the 7. And a very important result is that we do see that molecular tori are generally tilted relative to the host. The gas in the tori do not know about the orientation of the galaxy disks. And this random orientation extends on scales of tens of parsecs. It's not a parsec scale misalignment. It's really affecting the gas on the way it gets secreted on these large scales. Of course, there's a number of open issues in the field, and I will leave Almudena to explain how to tackle these open issues with ALMA, of course, but with other type of instrumentation like the Grantecan, VLT, and James Webb Telescope.
Okay, thanks, Santiago. And then let's move to Almudena presentation.
Okay, so I will share my screen now. Okay, can you see the screen?
Yes.
Yes, thank you. So thank you, Santi, for the very nice introduction on these highlights with ALMA for nearby AGN. So, but my talk now is going to be a discussion of the challenges we have in the next three or 4 years for nearby galaxies, and in particular, I'm going to restrict my talk also to radio-quiet AGNs. So basically, we identified 3 main challenges, and I think they are very related to the work Santi and I and our group is doing at the moment. So the first challenge is, as Santi said, we need to go from the single object studies to studies of representative of complete samples, so nearby galaxies, nearby Seyfert galaxies, and the already studied low luminosity AGNs in the NUGA sample. And the idea here is to actually get an idea of the morphologies and the kinematics of this AGN tori, and study the properties in terms of the AGN class, AGN luminosity, Eddington ratio, X-ray absorption, etc. The second challenge is to move to high luminosities, high AGN luminosities. There has been a few detailed studies of nearby quasars with ALMA, but most of them are actually associated with famous ULERCs. So we need to expand this. Another thing to take, another point to keep in mind is these quasars, even in the local universe, are more distant than Seyferts, and therefore we are not going to be able to resolve the torus. However, we can study the connection with the host galaxy. So we can, for instance, look at the molecular ionized outflows and also the circumnuclear star formation activity. And the third challenge here has to do with the all the modeling work that has been done in the past. So we will be doing some comparison with observations, and I think these comparisons will also help refine the models. And in particular, this is for application to intermediate and high redshift AGNs where we cannot resolve the torus. Oops, I'm not sure why. Oops. Okay. So let me start with the first challenge. So just to try to do some statistics on the properties of molecular dusty tori in nearby Seyferts. So this is part of the work in the Galactic Activity Torus and Outflow Survey, GATOS survey, that we've been doing in the last 3 or 4 years, where we are studying a volume limited sample of Seyfert galaxies. We selected the galaxies in ultra-hard X-rays because we believe this is the most complete way to select galaxies, although it's not completely unbiased. And as you can see here in this figure, we can probe a nice range of AGN volumetric luminosities, so almost 2 orders of magnitudes, getting close to the quasar border here. And also we can probe a nice range of absorption, X-ray absorption, going from completely unabsorbed objects to absorbed objects to Compton-K galaxies. And here you can see the comparison of the gatos that have been already observed with ALMA and the NUGA sample of low luminosity AGN. So putting these 2 samples together, we can have a nice range of AGN luminosities. So far we've obtained ALMA observations of the CO3 to 2 transition and also the continuum at 870 microns with the resolutions between 10 and 7 parsecs, which is what we need to resolve the tori. And we also have complementary observations with NOEMA and also with optical eye view instruments like Megara and Muse, and then in the future we'll propose for James Webb. So just let me give you just a preview of the work we've been doing in the last few months, and this is work that has been led by Santi. These are the first 12 Cipher galaxies in the GATO survey observed with ALMA. And we are showing here the central 100 parsecs of these Cipher galaxies. And we are showing here in color the CO3 to 2 emissions, the relatively cold molecular gas. And you can see that in all the galaxies, we are detecting molecular gas at the AGN location and also around. And although we are not showing here the large scale, this emission is also connected with the emission in the host galaxy. All the Ciphers are also detected at continuum at 850 microns, and we detect both a bright point source that we think is related, is probably synchrotron emission, and then extended emission, which is due to coal dust emission. And we are actually using this 850 micron emission to define the tori that we are detecting. And you can see here that these tori are relatively large, with diameters going from 20 to 100 parsecs. And actually, I would say that NGC 1068 that Santi described so nicely is on the small side of these tori. So we find really large toris. And then the masses, the molecular gas masses we derive have a range between 10 to the 5 and 10 to the 7. And again, as we saw with NGC 1068, is dusty molecular tori are connected to the host galaxy. But what makes them distinct is that they are, in most cases, not always kinematically and morphologically decoupled. Another important result is that the tori are perpendicular to the ionization cones and the radio jets, which is something that one has to expect according to the unified model. So now we have enough galaxies. So we put together the Cipher galaxies in the GATO survey. Okay. Together with the NUGA galaxies, we can start looking at some scaling relations. So here, for instance, we are comparing the column densities we get from ALMA, from the CO3 to 2 observations, and the X-ray observations. So we can see there is a good correlation between these 2 column densities. It's not a one-to-one correlation, but this is basically telling us that ALMA on the scales that we are probing right now is already resolving the bulk of the absorbing material. We can also look, for instance, at the molecular gas surface densities, and we can see that as we go to higher and higher Eddington ratios, these gas surface densities become smaller, and this can be taken as a proxy for the covering factor of this tori. And this seems to be in agreement with results that have been found in X-rays. And I don't have much time to talk about this, but then if there are questions later, we can answer those. So now if we move to the second challenge now, more luminous AGNs. So in the last few years, there has been some nice compilations of AGNs covering a large range in volumetric luminosities. And here we are just showing a comparison with the mass outflow rates. And we can see there is a good relation. So more luminous AGNs tend to have more massive outflows. And there is also a difference in terms of the outflow phase. And what is interesting here is that the molecular phase, at least out to 10 to the 45 AGN luminosities, dominate these mass outflow rates. At higher luminosities, it's not clear. But one problem we've had in the past is that since these are compilations, in most cases, the different outflow phases are observed for different objects. Here I'm showing just one exception. This is a relatively nearby quasar, which is also classified as a ULERC. And what is interesting here is that the ionized outflow is taking place on very large scales. It's almost at 20 kiloparsecs from the northern component of this interacting system, whereas the molecular emission is concentrated in less than 1 kiloparsec, and there is evidence of an outflow on these scales. So obviously these two outflows cannot be part of the same episode. So this is also giving us some information about the episodic nature of the AGN phenomenon. So to do this in a more statistical way, this is a work that is being led by Cristina Ramos Almeida. This is right now it's only a pilot study. So she chose 7 type 2 quasars, and she's observing them with ALMA at 0.2 second resolution, which because they are more distant, and now we are probing scales of a few hundred parsecs. The main results here very quickly is that 5 out of the 7 are detected in cold molecular gas with very diverse morphologies. There is also evidence for non-circular motions in all 5. And the kinematics are consistent with outflows, but these outflows, what we are finding is that they are not as extreme as the molecular outflows in ULERCs. So stay tuned because there will be a paper coming out in the next few months. And just the last challenge very quickly that has to do with the torus models. I'm not going to go into any detail, but just let me say that in the last 30 years, there has been a really amazing evolution in the models that has been driven not only by observations, but also by computational capabilities. So right now, as Santi said earlier, we are going from static torus models to static disk wind models to things that are really hydrodynamical models. So these kind of models now allow us to compare their predictions with our observations, because now we have the physical resolution in our observations to do these comparisons. So here's just a prediction for the mean velocity from one of these models from David Williamson. And this is just quickly some work that we are doing at the moment where we are comparing the mid-infrared and far-infrared morphologies with model predictions. So these are still the models, and these are the models degraded and repixelated and all that to the observations that we are finding, that we are getting. So this is another way to, as I said at the beginning, to refine these models with this detailed comparison. And since I'm sure I'm running out of time, I'm just going to leave our conclusions here. But again, I just want to re-emphasize the point that Santi made at the beginning of the talk about the importance of the torus, that now, of course, we understand more like a disk and a wind. The importance of the torus, not as an isolated structure at the center of a galaxy with the AGN phenomenon. This is more than that. This structure is the central structure in the gas flow cycle. So now we need to, the torus, understanding the torus allows us to understand how the gas is being brought from the host galaxy to feed the supermassive black hole, so what is being called in the literature the feeding phenomenon, but also this gas is driven out by the AGN in a wind, so it's going to participate in feedback processes. And that's all. Thank you.
Okay, thank you, Santi and Almudena for this interesting talk. We have about a couple of minutes for questions, and I have a question for you, any of you. Why the torus is misaligned with the galaxy disk? Is there any reason for that?
Santi, you want to answer that?
Yes. Well, there are several explanations. We are in a very 3D environment, so there can be a accretion that is coming to the torus in a perpendicular or misaligned direction, because it's a very 3D environment. We have to be aware of this. So there can be accretion that destabilizes the inner structures. There can be also effect of feedback, radiation pressure. The jet can misalign also the structures. So there are several mechanisms. Even also it has been some discussion about gravitational effects that can propagate and create these warping structures in the inner tori. So there are several explanations, but I have to say this is still an open issue and it's being discussed because this is a very important thing. We have to understand that if the disk gets misaligned, as we observe, the feedback is more efficient because it's not, I mean, the tori are not perpendicular, are not coplanar to the galaxy host. So the feedback is not coming in a perpendicular direction, but it can be oriented along the axis. So there's a stronger coupling between the edge and wind of the jet and the gas inside the disk.
Okay, and do you find any correlation between the energy or the luminosity of the outflow and the mass of the torus?
I don't think there is a correlation between these two variables. There is some correlation between the outflow rate of the mass outflow rate and the AGN luminosity. That has been discussed in the literature, but on this very small case, I don't think there is a correlation between the AGN luminosity and the mass. We don't find that with our statistics, a correlation, right?
Well, we have a comment of Miguel Sanchez Portal that say that the large size of the tori found by ALMA confirms that what was anticipated by including far infrared data in the torus models. So,
yes, yeah. If I may say something, yes, of course. I think from the spectral energy distribution modeling, we were getting a lot of hints that the torus had to be larger than the people were finding with near and mid-infrared interferometry. But of course, we didn't have the proof, right? The images, but when we were doing the modeling, we needed this larger tori. And I think when I remember a few years ago, I presented these results by Santi at a conference, and all the mid-infrared interferometry people were like almost upset that the tori were so big. Well, in that case, it was only NGC 1068, but we did have some, and actually the literature was back and forth on the size of the torus. So some people were thinking it's very small, some people were saying very large, even 100 parsecs, and now we are finding some of these that are as large as 100 parsecs. So, yeah.
Well, we do have more questions, but I think that we don't have more time. But you can answer the questions in the.
One second.
Yes,
okay.
And then we have to move. Well, let's thanks again to Santiago and Almudena